Hello, everyone. Hope you're doing well. This is a little bit of a video of where have we come from and where are we going? This is the halfway point of our class now and the very last video of week 5 as we start going into this. And I even thought of including this as the first video of week 6, but I kind of looked at where the videos a lot ended up kind of falling and decided this would be a very good ending here to week 5 as we start moving into functional vector spaces. You can see kind of the subtitle here of functional vector spaces. And in particular, I have a little epithet to go with that just reads Intro to Fourier Series. That's what we'll be talking about today as kind of a where have we been coming from and where are we going with this material. And the reason for this is this. When I was younger, and many personalities are like this, you could just take your brain and make it a receptacle of information. You could just keep kind of pouring it in, keep pouring it in. But I've recognized that as I grow older, I become a little bit more reluctant to just remember things or try and know all of the things just for the sake of knowing it. Again, many personalities soak all of that stuff in. They are trivia knowledge receptacles. They just take in everything that they can get. I'm not a trivia person. I don't typically hold on to things unless I have a reason for holding on to it. So a good thing that I think is important for this course, and we'll see a little couple of seeds here and there kind of strewn throughout as we go through this latter half of the course, is what is all of this for? What was the purpose of all of this? What is the reason for trying to develop a notion of a space that involves functions as well? A lot of what we've done this week hopefully has started to justify some of the things that we've been doing. In particular, you might notice that there's a lot of solutions to differential equations going on here that are very important to us moving forward. But even those differential equations topics that we've been covering have very limited uses. For example, looking back at the fixed point theorems video, the example that I gave works very well in that niche scenario, as does the scenario that I present in the homework. But you might have noticed that, oh, I could have gone through and done this in a slightly different way, or what if I change this part of the problem a little bit? And typically, those types of formulas need very stringent types of frameworks in order for this particular method of solution to work. I give them to us so that we can see that this is what we're thinking of when we think of an operator, or this is what we're thinking of when we are trying to make all of these functions piece together. But there is one topic that all of this was developed for that has changed the face of analysis for 300 years, and it is exactly that of the Fourier series. This is a series of functions that is meant to approximate a given function f of x. The definition of it is this. Given a function f of x, we define the Fourier series of f to be this particular series of functions. Notice something interesting and different about this than something like, say, a Taylor series. A Taylor series is a way for us to approximate a function based off of the derivatives of that function. It requires your function to be smooth, that is infinitely differentiable, on whatever your point is that you're attempting to intersect. And if you ever try and go off and maybe make a part of your function non-smooth and a part of the interval you want to approximate in, your Taylor series is going to fall off. So it really wants your function to be smooth in the given interval in which you want to approximate the function. And what it does is it takes at a particular point, maybe you call it A, you say, okay, well, I can go through and plug in that point A into the function f. And then I can plug it into the derivative of that function if I know that a derivative for that function exists. And then I multiply that times the function x minus a. And you might know this formula alone as the linear approximation of a function at a given point. If you know that it is for one-time differentiable, then you can use this as the best approximation of it or as a good approximation, a tangent line approximation for the function at a given point. In particular, if I add over this 1 factorial, then there's no real change here. Recall that a factorial multiplies a number all the way down to 1, so 1 factorial is 1, whereas 2 factorial would be 2, 3 factorial would be 3 times 2 times 1, which gives us 6. And continuing this formula all the way down, we can actually get a better approximation for it, this function, given that we know that the concavity of the function matches the original function at a as well. So this is saying, okay, not only is this a tangent line approximation, this is kind of more of a tangent and concavity matching parabola. that matches the function at this given point. And we could keep going with this to get an entire series, an infinite series. And given certain conditions on the function, this actually is equal to the function at a given point f of x, at least if we take the limit of these partial sums. And the hope for Fourier series is to do the exact same thing, but you might notice a few key differences. The thing that I am using as kind of like my linear combination pieces, my vectors, my the parts of the functions that I'm adding together that aren't constants are 1 over here, then x minus a, then x minus a squared, x minus a cubed, and so on and so forth. There's an interesting question here, and we may not come up with this naturally, but for a lot of dealing especially with functions where sines and cosines come up, which as we'll see in an upcoming example, we might want to make our linear combination pieces of these series equal to cosine of, say, 1x, 2x, 3x, and sine of x, 2x, and 3x. This turns out to be extremely helpful for a reason that we'll see in an upcoming example. So we define the Fourier series of a function f to be exactly this piece. There's still a unit component. Think I'm still working on some sort of part of the function that is where f of a times 1, this is a naught over 2 times 1, plus this whole series of stuff going on here with linear combinations of cosine nx and sine of nx. The Fourier series of f is this series where the coefficients an and bn are given as these values over here. Now, in the future lecture and also in our linear algebra courses, we've talked about inner products. And depending on your proximity to your linear algebra course, you may recognize these as an example of a inner product of the function f of x with cosine of nx on a space like the continuous functions going from negative pi to pi. That this is an example of one of those inner products. A typical inner product for the continuous functions is indeed the integral of the product of the two functions that you're taking the inner product of. Think you're multiplying component-wise each and every one of the points of the functions together, much like how you would in a dot product. That's essentially where inner product generalizes, is that the dot product in real numbers becomes the inner product in continuous functions. So these are inner products here. So where this sort of formula and theory comes from is linear algebra. In particular, it uses the fact that the set of all functions of the form cosine nx and sine of nx are an orthonormal set inside of this continuous functions from negative pi to pi. In fact, if you add in a normalized unit function, like something that normalizes 1, which ends up being 1 over square root of 2, if you add that into the set, then what happens is it becomes an orthonormal basis. Again, you may need to go back to linear algebra to remember some of those terms, but we'll also talk about them a little bit in week 9 of our video lecture, so kind of giving you an idea of kind of where we're going here. But when you put all of these inner products together, this ends up being just a sum of projections of these functions onto a linear combination of functions of the form cosine x, sine x, cosine 2x, sine of 2x, and so on and so forth, all the way, and also including 1 over square root of 2. So this Fourier series is a way for us to perhaps rewrite a function. However, there's an interesting question here, which is, do Fourier series actually do anything? Notice that I never said f of x is equal to this function. Notice for like Taylor series, we needed some parts of the conditions on f in order for this to be a good approximation. This, for example, would not be a good approximation for the function absolute value of x. The absolute value of x function, if I try and center a Taylor series at x equals 0, well, one, I'm not getting very good derivatives of that function at that point. So this is not a good approximation. But even if I pick a point like x equals 1, do you know what it's going to do? If I take a Taylor series around the point x equals 1, then the formula does not know apart the absolute value function and the linear function, the smooth function on the interval that I'm approximating. So if I wanted to find the Taylor series of the absolute value of x function at the point, say, x equals 1, then what would happen is what it's going to give me is the line that goes through the point 1 comma 1. Because that's the local information that I'm given there at that point, x equals 1, is that the way the Taylor series reads it is it says, oh, at x equals 1, my y value is 1, and you know what? My slope is 1, so I know it looks like a line. And all of my other derivatives of this are 0 here. This has no concavity. It has no jerk, the third derivative, and it has no derivatives past that. So the Taylor series is going to look at that local information here and say, oh, when I approximate this, I'm just going to give this line. But maybe you actually wanted the absolute value of x. So Taylor series do very well with a very limited amount of data, just all of the local data, all of its derivatives at a given point, and then attempts to extrapolate that to the best fit smooth function that it can give. On the other hand, a Fourier series does not need derivatives. It also is not gathering from particularly local data. You can notice here that the Fourier series is taking the function and multiplying it times another function and then integrating it against that function. That's requiring global information all the way around. The Fourier series of the absolute value function actually returns the absolute value function. So that's an example of something the Fourier series can do a little bit differently. It also does not need derivatives of the function. And instead of asking for derivatives at a given point, it asks for global information on the entire function. Now, what's the reason behind all of this? What's the point of working with Fourier series at all? And the reason is that sometimes we come up to some examples in partial differential equations that ask questions like this. A bar whose surface is insulated has a length of 3 units and has a diffusivity constant of 2 units. If its ends are kept at temperature 0 and its initial temperature throughout is given by the function u of x comma 0 equals 25, what is the temperature of the bar at position x and at time t? Now, 300 years ago, this is exactly the question that they were attempting to answer. They had already come up with an equation to help us deal with how this sort of thing is supposed to work. That namely, the temperature of a thing, of the rod at a given position, the derivative of that with respect to time is directly related to the concavity of the temperature function with respect to changes in position. That's exactly this heat conduction formula that we have right here, is that there's a direct relationship between the derivative of u with respect to t and the second derivative of u with respect to x. That relationship is dependent on the type of material that you're using to build the bar. That's why that kappa is there, right there, in kind of like the middle part of that equation you see right down in here. That kappa is known as the diffusivity constant. It's essentially something that changes depending on the type of material that you're using to build your bar. Is it something conducive to heat or movement of heat through it? If so, that diffusivity constant is going to be a bit higher, and you'll see changes in the temperature with respect to time happen more quickly, given an initial position. But the answer how to solve partial differential equations is much more difficult than the one of trying to solve ordinary differential equations. Even when we solve ODEs, we typically are looking at very specialized classes because those special classes have types of solutions that are associated with them. For example, whenever we deal with second order linear equations, we typically are asking for them to have constant coefficients whenever we're trying to deal with them in ODE class. And that's because if we start introducing things that are not constant coefficients, things start getting a little bit wonky. Our solution techniques are not as nice anymore. At the end of the day, many engineers and other applied disciplines are very okay with just saying, okay, well, I'm just going to get a kind of a numerical approximation of a solution to this differential equation. And they move on from there with a given understanding of a tolerance that moves with them through the problem. But the heat conduction equation, a partial differential equation, has a solution. And there is a mathematical solution technique for us to kind of get there. In particular, we're attempting to solve the formula, which is the derivative of u with respect to t is equal to some sort of diffusivity constant times what's known as the Laplacian of the temperature function. And that Laplacian is the sum of all of the second derivatives of the function with respect to the spatial variables. Notice here that I've not quite given you what these variables are, except up here in the question. So our position x is kind of like saying, okay, starting at a point x equals 0 for our rod, I can go all the way over here to, let's say, x equals 3 for the length of 3 units. So I do know that my x value goes from 0 to 3. My t value goes to any value that's greater than 0. I have a point that where it starts at t equals 0. And then at any point beyond that, I would like to know what the temperature of this is. So those are initial conditions. What I'm talking about are boundary conditions for this partial differential equation. Now, I want to emphasize at this point that the contents of this lecture are not something that I'm going to ask you to read anything about, or I'm not even going to put quiz questions on them. I'm not going to put homework questions on them, and you won't see them on exams. This is totally a day for us to see where we've come from and where we're going. But hopefully this is enough of a grasp for you to think, how do I solve for temperature functions of a given rod if all that I know is its diffusivity constant and what its temperature begins at? And that's exactly what we're doing here. What we're going to do is use a method of separation. You may be familiar with like a separable equation where you try and separate equations on the left and on the right. We'll do a similar thing here. We'll start by assuming that our solution to the partial differential equation is a product of two single variable functions. The goal of this is to boil down PDEs to a level of ODEs so that we can use similar topics that we've talked about in ODEs to solve this partial differential equation. So here, I will write u is equal to x times t. I'll use capital letters to talk about these functions that are not the solution function. Capital X is a single variable function that relates only to the spatial variable little x. And capital T is a single variable function relating only to the lowercase variable t. So notice that these functions x and t are constant with respect to changes in their other functions. And that's something that's pretty important for us here. You'll also see us make an assumption at some point that u is a bounded function. Again, I'm not going to go through every single step here because this is not something that we need to know. But I do want to show you a little bit about what these sorts of solutions might look like for this type of partial differential equation. So here we are. Just to start from the beginning, we have our general equation here. Derivative of u with respect to t equals, I've gone ahead and plugged in 2 for the diffusivity constant, times the second derivative of u with respect to x. Assuming that u is equal to x times t, I could go ahead and plug that in. Again, taking the derivative of u with respect to t means that x is going to be constant, so it just kind of gets to stick around. So in black, you can see here, this is the sort of equation that I would end up with. If I go through and divide to separate the variables of these equations with respect to t and x, then I get an equation that looks a little bit like this. And I wanted us to notice something interesting about this. Here we have on the left an equation that only changes with respect to t, and on the right we have an equation that only changes with respect to x. That means that if the equation with respect to x is the function that changes with respect to x, then the function on the left is not changing. This t prime over 2t is not changing. Well, what does that mean? Since these two functions are equal, that means that the x double prime over x, that also cannot change with respect to x, because these two things have to be equal. We know that first equation that is only written with respect to t does not have x in it, so it is constant with respect to changes in x. And because these two functions are equal, the whole function is constant with respect to x. The similar thing can be said about changes with respect to t, which means that this function is constant with respect to any changes with respect to x and t, and we can call that constant c. We now have two ODEs to go through and solve. One of them has to do with x double prime over x equals c, which we can go through and solve using that second order ordinary differential equation technique. And this one over here might be a little bit more familiar to us. T prime equals a constant times t. If I had just written t prime equals t, we recall that what we'd be doing here is solving for an ordinary differential equation, asking what function, when I take its derivative, gives me back the function I plugged in. Well, that's going to be the function e to the t. And if I plug in a function here, 2 times c, that to be multiplied times it, well, then I know that that has to be in the exponents because of the chain rule for that exponent. So I get my function t to be equal to 2 times c times t. Now, for the second ordinary differential equation, what I end up figuring out is that this, due to my ODE stuff, going back to this, depending on the value of c, this could be either a positive value of c or a negative value of c, and our solution becomes a lot different depending on whether it's positive or negative. It turns out to be negative, and this is due to the boundedness nature of the temperature function. Briefly, if I had chosen c to be positive, then this would actually be an unbounded temperature function. So I end up having to choose that c goes to be negative, in which case x is going to be equal to c1 times cosine of the square root of, I have to write negative c inside of here to be able to take the square root of a positive number, since I know c is negative. And then adding that to c2 times sine of square root of negative c times x. By the way, this may be a point where you start recognizing that cosine and sine becomes interesting. We need cosine and sine to start solving this part of this differential equation. Anything that involves this Laplacian, especially, is going to have a cosine and a sine as part of its function. Well, there's my x, and there's my t. And then to make things a little bit easier so I don't have to tote around square root of negative c, I'll let lambda be square root of negative c. So going through and substituting that in everywhere. So like this square root of negative c becomes lambda. This one does too. This one had a c in it. So I have to go through and get negative lambda squared when I go through and rewrite that. And I end up getting this as my solution. U of x of comma t is equal to the product of the two functions that I just found, x times t, which is equal to e to the negative 2 lambda squared t times C1 cosine lambda x plus C2 sine lambda x. Now, there are a lot of constants in this function, and more than we're typically used to having, even when solving ordinary differential equations. But gratefully, we have a proliferation of boundary conditions to go through and plug in. For example, we know that when x is equal to 0, that our initial temperature, or our temperature at that point in the boundary is equal to 0. Going through and plugging that in gives us one of our constants. Plugging in x equals 3 actually gives us a value for lambda. In fact, it gives us more than enough values of lambda, because what I end up having to solve when I plug in x equals 3, and I'll spare you the details here and just kind of cut to the chase, is that I need to be able to solve sine of 3 times lambda is equal to 0. But there are infinitely many solutions to that. The value of lambda could be pi over 3. It could be 0. It could be 2 pi over 3. It could be negative pi over 3. The great thing about sine of negative pi, however, if I were to plug in negative pi over 3, is that it is the same value as sine of pi. In fact, even if I put different constants in front of each and every one of them, then I would still have essentially that these sine of negative pi times x and sine of pi times x are the same function, just maybe with respect to a change in plus or minus. So I end up only needing the non-negative values of lambda. In fact, only the positive values of lambda are really the ones that I need, since if I had plugged in sine of 0 for this and get a 0 for my lambda, then what I end up getting is sine of 0 for my entire function, even when I plug the x value back in. So I end up only needing the sum as n goes from 1 to infinity, can really even write 1 here, of functions of this form. A constant, C2, because the first term is gone thanks to C1 being equal to 0, times e to the power of, I had found a solution to lambda, so I've gone through and plugged that in. The n pi over 3 is squared and stuck in right here, times t, times the function sine of n pi x over 3. Now, any solution with any value of n is a good solution to that. You may recall the principle of superposition, which says that if you have a bunch of solutions, then a linear combination of those solutions will also be a solution to u of x comma t. So if all of these are solutions, regardless of the value of t, then what I end up getting for a solution of this differential or partial differential equation is here. The sum then goes from 1 to infinity of a constant times some exponential function times sine of n pi x over 3. Now, there's one more condition that I haven't quite plugged in yet, and I know that this is blistering. Again, you do not need to remember many of the details here because I'm not going to be asking questions about it. But when I plug in t equals 0 to get my last initial condition of u x comma 0 is equal to 25, this is my initial temperature of the function, then what I end up getting is, well, when t is equal to 0, I have that this is 25 equals the sum, as n goes from 1 to infinity, of some sort of constant, c sub n, times e to the 0, which is 1, times sine of n pi x over 3. And what this is asking me for is, are there constants c sub n such that I can make a linear combination of all these sine of n pi x over 3s and take a limit of those as I continue adding more and more sine terms to it, so that eventually what I end up getting to is something that approximates the function f of x is equal to 25. This is where the notion of Fourier series comes from, is that it appears naturally as a part of solving partial differential equations. Let me show you something real quick here. So here's what I've done. I've gone through and found and calculated those sine coefficients, the Fourier coefficients using the Fourier series. And I want us to notice something interesting about it. Now, first, what I've done, just to explain what's up here on the screen right now, the blue line, I have taken the function g of x equals 25 and noticed that it was pretty big. So I brought it down to y equals 1. But I could have done the same thing by just multiplying everything through by 25 at the end of the day. Another thing that I've done is I have gone ahead and drawn these vertical lines, this one over here for x equals 0, and this one over here for x equals 3. Imagine these as the temperature ends of the bar that we're attempting to find the temperature of, and that this right here is the initial temperature for that. This is that initial temperature, which we'll just go ahead and normalize to be 1. With g of x equal to 1, I've gone through and solved for the Fourier series of this, and I've put them together here in this series. Notice what happens is I keep adding more and more terms to this series. Here, this is one with just one term. Again, n equals 0 is actually going to be 0 in this case because it's sine of 0 when I plug in n equals 0 here. Or actually, nope, I take that back. When n is equal to 0, I actually get pi x over 3. So this is just two terms of that series. If I add in a third term, then it looks a little bit better. If I add in a third term, notice what's happening. There are parts of this function that are kind of still really far off from the approximation, but notice that there's actually no way for the 0 to come all the way up to 1. The reason is these are a linear combination of sine functions, and sine of any value, if we plug in 0 for x, is going to be 0. So you're always going to be stuck down here. Similarly, because of this pi x over 3, you're also going to be stuck down here at 0 at x is equal to 3. If I plug in x equals 3, I have sine of pi times 3 over 3. That's sine of pi, which is 0. No matter how I multiply that times a scalar multiple, I'm still going to get 0 for that. But everywhere else on this function, I'm getting something that is kind of like a continuation or a continuous approximation only made out of linear combinations of sine functions. That looks a lot like this function. Let's bump this up to 10. Now that's an approximation right there. And you can imagine what something like this would look like if I continue to make this happen. What I'm getting is something that is a close approximation of this function of 25. And indeed, if I ignore the endpoints, then at any given point on this function, I would eventually converge to 25 if I considered, say, just a slice of all function values at a particular x point. Because if I took this all the way to, maybe this will break it, but let's see if it doesn't. If I take this all the way to 100, I mean, just look how incredible this is. We are getting better and better approximations, and these little wiggles that you see at the very end, they're getting pushed to the sides. Essentially, eventually, they're all going to become so narrow that they don't even matter for each of the vertical slices we're going to be making to see where these sequences go. And seeing just how close these functions are to the function of 1, we are already within, with just 100 terms here, we're already within about 5 thousandths of the function here, and just looking at this kind of part. So you could see how if I continue to add more and more terms to this, eventually what I end up getting to is 25. So I can now go back and plug in those constants. And I have a solution to the heat conduction equation with respect to the boundary conditions that I was given. That's the whole idea behind partial differential equations. But remember that I said that not all Fourier series work neatly with this. It turns out that it works nicely for continuous functions, and a lot of that is due to the linear algebra stuff that I was talking about before. For linear algebra, you can write this down as a projection using inner products onto specific functions. And again, we'll talk about that a little bit more in week 9. But there are entire classes of functions where it is still unknown if Fourier series end up approximating the function f of x. Just like how the Taylor series for absolute value of x does not approximate it everywhere due to some constraints that it has, we have to ask the question, do Fourier series approximate any type of function that we might use? Now, the answers to that question are not something that is here in this class. This class gets us ready to answer those sorts of questions, especially if you're ending up going into a more harmonic analysis. There are other branches off beyond that point than just Fourier series, but to me, this is the most applicable one for what the content of this class is meant to do. And historically, it also is the most truthful to where these sorts of topics came from. Why did we develop this in the first place? All of this sort of machinery that we've been building about metric spaces started from taking a look at Fourier series. And all of the things that we're going to be learning about started by taking a look at Fourier series. So we'll be talking a lot about functional vector spaces as we come into these next few weeks. And the reason is we want to basically be able to answer this question. When do Fourier series approximate the function? The goal for that, when are we able to get good solutions for a differential equation given initial conditions on our whatever it is we're looking at? Because these partial differential equations don't just help us answer heat in a rod, they also tell us the vibration of a string. They also tell us the flow and the shape of water, which you may know as the Navier-Stokes equation, which have gone unsolved for over 100 years now. So having more knowledge about these types of functions tells us more about where they could be applied and allows us to understand more the very flows of nature. Functions describe everything around us. So if we're able to find a function that is derivable from these partial differential equations that we know are true given the type of liquid or the type of situation that we're in, then what ends up happening is we know a little bit more about the world around us. I got excited and ended up not even using the slide that I had made to talk about the exact things that I was talking about. But this is it in written form. So you can kind of take a look at through all of this to see what all of this was developed for. So what are the things that we're going to be looking at a little bit differently as we move forward? Well, we're going to want to switch out our vectors. Recall that we've been able to think about vectors, or rather, we've been able to think about our elements inside of metric spaces as numerical vectors, like 1, 2, 3 inside of R3, the coordinate 1, comma 2, comma 3. We've also been able to think of it as sequences, kind of a form of like instead of R to the n, it's like an R to the infinity, a sequence type of way of looking at it. And we've talked a little bit as well about how functions might be making sense here, especially on the very first day when I was starting to give some examples. I used functions as some of the examples of metric spaces. We're going to want to focus more on the function part in what is to come. And this is to help us get a little bit closer, just a little bit in that direction of, are we able to say anything about what Fourier series do? Again, those answers are not things that we're going to be able to address. We're just going to stick to the theory for now. And it's good that we do that because not all of us are going to go into our harmonic analysis route where we talk a little bit more about Fourier series. Some of us are going to go on to other analysis things. Perhaps you have an interest in measure theory or something else. This is a great way to get started with that. Perhaps your interest is not really in analysis at all, but rather its applications to another field, maybe biology or engineering. For some of you, you are going to have different things to take out of this series of lectures. But this is just one thing that I think is extremely cool, accessible to where we're at, and helps us get to know a little bit more about why we should be learning the things that we're learning. Another neat thing about Fourier series is that we want to be able to find them for all different types of functions. If you're able to find a Fourier series of a function like f of x equals x given right here, a good question is, how could we use this to find the Fourier series of something like f of x equals x squared? Well, something that you might consider doing is this. First, let me mention something. This cosine of n pi oftentimes has a little bit of an easier way of describing it to us, which is the function -1 to the n. And the way that I can see the equality between these two things is that cosine of n times pi is something that kind of depending on your value of n, which here n is an integer since it's indexing from the sum, that when cosine of is you're looking at cosine of n pi where n is odd, then you're looking at like cosine of pi, cosine of 3 pi, all of which are -1. Whereas if I looked at cosine of 2 pi, cosine of 4 pi, those are values where the cosine value is 1. So that matches term for term for this function -1 to the n, which is -1 when n is odd and 1 when n is even. But the question is, could I use this to find the Fourier series for f of x equals x squared? And something that I might consider doing is attempting to integrate both sides. Why would I do that? Well, take a look over here on the left-hand side. What I end up getting is something like x squared over 2 plus a constant like c1. Now, over here on the right-hand side, I'm not quite sure what I get. Now, there's a few ideas that I have. One of those ideas is I could integrate each of these individual functions before we get too frightened by that. N here is just a constant with respect to each index in the sum. The only thing we'd be integrating is dx. N is going to be held constant. In which case, all the thing that we're integrating is sine of n pi x over 2. With the chain rule, you get another 2 over n pi out of that, and you get like a negative cosine of x. And that's essentially the only difference. But I could integrate each term, but what about integrating the entire series? How would I be able to differentiate that? And something that comes immediately to my mind when I see that is, am I able to switch those two things? Is it possible for me to take the integral of the sum of some sort of given functions, let's call them f sub n of x, and say that this is equal to the sum of the integral of f sub n of x dx? Is it possible for me to switch around these two things? This is definitely possible when I'm looking at, like, say, finite sums. Like, for example, if I have f plus g and I'm integrating it, then I can take the integral of f plus the integral of g. But I'm not sure if I can do that when there's a limit involved. This is a limit of partial sums. And how does the integral sign work neatly with the limit? This turns out to be an extremely interesting question and one that is very hard to solve. This is actually the birth of something called measure theory. And that's another direction that we could be taking this material. We won't get the chance to talk about measure spaces in this class unless maybe I get a little bit excited at the end and try and give it as an optional video of some sort. But it's a decent question to ask, when can I take the sums and the integrals and switch them around? We'll talk about that a little bit here and the end of next week. Because if we could switch these around, then we can just integrate both sides, integrating each of these terms to get some sort of integral of this function, whatever this is, plus c2. And once we solve for the constant and multiply through by 2, what we end up getting is x squared. And it turns out that that would be exactly the Fourier series of f of x equals x squared. So if I know one of these functions, then I could actually find a Fourier series for a whole class of functions by utilizing integration and differentiation to help out. So the issue with some of these, and the reason that this may not work, is that we're kind of asking the question, is it true that if I get that the functions f sub n converge to the function f, is it true that the integrals do the same thing? And there are reasons to say that that isn't true. Let's take a look at these functions, for example. Here I am given some little triangle functions. These functions are defined as given on the piecewise function here, but I think it's better to see them as pictures. They're little teeth functions. There's one tooth, and the way that they're formed is that as I bump the value of n up, then what I'm doing is I'm scrunching together this tooth a little bit, but I'm also making it taller. So if you can imagine what these functions are doing, they're starting with a tooth like this, and then they kind of move closer and closer to zero while also squinching together and making the tooth taller. Now, notice what's happening to each and every point here. You might think, oh, this is a lot like that series of functions that we just saw with the Fourier series, and you'd be right. These functions here, these functions are all going to converge in a form called pointwise, which we'll talk about next week. Pointwise to the function f of x is equal to 0. So these are going to converge pointwise to f of x equals 0. But they do not converge uniformly, which again we'll talk about next week. Basically, the way to think of it is that the spike is too tall to fit within any epsilon neighborhood of the x-axis throughout its entire region. But notice that because of this difference, converges pointwise but not converges uniformly, that I could say that these functions f sub n, which are the functions given here, that these converge to 0. But what about the integrals of the f sub n? Do they converge to the integral of 0, which is equal to 0? We'll take a look at the area under the curve for each of these functions. This is a triangle, and the formula for the area of the triangle is 1/2 times base times height. 1/2 times 1 over n, the base of the triangle, times the height, which is n. This area is equal to 1/2, regardless of what f sub n we choose. So if I take the limit of these integrals, that's going to converge to 1/2 as well. And 1/2 does not converge to 0. So that is kind of the issue that this talks about why we don't necessarily just integrate immediately what we have on the previous slide, is that just because functions converge to a particular function doesn't mean that their integrals do. So we have to be very careful whenever we make some of these steps. There's even another issue here, which is that you can get uniform convergence. You can get this function f sub n of x equal to 1 over n, and you can get a uniform convergence through that, but the interval of integration is unbounded, in which case you similarly have an issue. In this case, for example, the functions f sub n, which is 1 over n, converges entirely to the 0 function. Again, when I write 0 here, I mean the 0 function, the function that is 0 everywhere. But the integrals of these f sub n's are equal to the integral of 1 over n. And now I have to ask what my interval is. Because the integral of 1 over n depends on if I'm looking at a small region, like the integral from 0 to 1, or if I'm looking at all of the real numbers. For example, if I'm integrating this from all of the real numbers, then this is going to be equal to infinity for all n, which does not converge to 0, which is the integral of the 0 function. So that's another example of if my interval of integration is unbounded, then it's potentially possible that I still don't get convergence here. So we're going to have to talk a little bit about how can we combine notions of things like compact. You're going to see the word compact a ton in these next few weeks, because that's a huge concept for us, especially when we start talking about functions, is some sort of notion of whether it be closed or bounded in the real line, or totally bounded in the metric space area. That's going to be a big deal for us. One last example, just to kind of get us into seeing that these convergence of functions are actually interesting in their own right, even without any of the applications that we've been talking about, is this. We'll use this definition a good bit in some of our homework assignments, but we'll define the characteristic function of 1 sub s of the set S to be defined to be 1 on the set S and 0 elsewhere. So this is going to be a characteristic function, which is piecewise, which is equal to 1 if x is an S, and 0 if x is not an S. For example, if I wanted a graph of what 1, 0, 1 looked like, then it would look a little bit something like this. Here's 0, here's 1. This function would be equal to 1 anywhere inside of that interval, including the endpoints, but it would be equal to 0 elsewhere. Not a continuous function. Kind of looks like a step, doesn't it? It's a little bit kind of like a step function. You can imagine making step functions out of this. But this characteristic function ends up being very important when we start trying to deal with these types of convergence for functions. We'll use characteristic functions a good bit as we go through that. For example, we might use it in this case. Here, for the function f1, we might start by writing just the interval. That exactly what I have right down here, 1, 0, 1. Then we might take a look at the functions f sub 2, which is 1, 0 to 1 half, and f sub 3, which is equal to 1, or the characteristic function going from 1 half to 1. But I might notice what else is going on with these functions. I'm adding kind of a middle point here. This one going from 0 to 1 here, and then one function goes directly from 0 to 1 half and then stops. And then the other function starts at 1 half and then comes back down to 1. I could keep going with each of these functions, but maybe you could start imagining what these stepwise functions look like. The next one, for example, you're going to get functions that have a little fourth right here, a little fourth right here, a little fourth that's to the right of it, and then a little fourth that's over here at 1. This one starting at 0, this one ending at 1 half, this one starting at 1 half and going to 3/4, for example, and then this one going all the way from 3/4 to 1. Notice that these functions converge in area, the area under the curve, because the little rectangles that they make get smaller and smaller, but they do not converge even pointwise. Because at any particular x slice that I'm going to get in some length of those functions, I'm going to be able to get something that is equal to 1. One way to think of that, why that might be true, is that if you take these functions of this form in the way that I've given them up here, and sum them as k goes from a particular beginning and ending point, k equals 0 to 2 to the n minus 1 for this one, then the sum of this is actually the whole characteristic function from 0 to 1. That's basically saying if I add all of these functions together, then that's modulo a few like endpoints that are all the same together. But that's saying that if I take all of these functions and add them together, then what's happening is at no point am I ever going to get to converge all the way to 0. But also I'm not going to be able to converge to 1 because there's going to be like a ton of functions where I'm at 0. So there's infinitely many functions where I'm at 1, infinitely many functions where I'm at 0 for any given x value. So we'll talk a little bit more about these sorts of examples as we get closer to it. Here, again, this is just a glimpse at what we're getting at. We're going to be doing more in terms of the definitions, in terms of everything, but this kind of lets you know kind of where we're going with all of this sort of stuff. But that'll do it for me today. Thank you so much. Have a wonderful day.